we'd like to find the value or values of x at which the piecewise function shown is discontinuous. Well, we can see the function on the next page. We put the left-hand portion in pink and we put the right-hand portion in purple, partly for dramatic effect, but also to show the two different domains. This is the first piece of the piecewise function. This is the second piece, but it is all one function. Okay. Now, looking at this, we see that all x values less than 2 are governed by the polynomial function 2x minus 2, and all x values greater than 2 are governed by the polynomial function 4 minus x. So therefore, for all these x values, we have a continuous function. The only possible problem, if there is one, is at an x value of 2. So what we're going to do is ask ourselves whether or not the limit as x goes to 2 of f at x exists. Well, from the left-hand side, we see that the limit, as the x value gets closer and closer to 2, the y value gets closer and closer to 2 as well. So from the left-hand side, the limit exists. Looking at the purple one, as x goes to 2 from the right-hand side, the y value also gets ever and ever closer to 2. So we can say that the limit exists and that the limit as x goes to 2 of f at x is 2. Well, now let's ask ourselves if f at 2 actually exists. Well, since 2 is less than or equal to 2, recall our original function, for any x value less than or equal to 2, the governing statement is 2x minus 2. Well, since 2 is in that left-hand domain, we see that f at 2 is equal to 2, and therefore it's safe to say that yes, f at 2 actually does exist and equals 2. Finally, we ask ourselves, does the limit as x goes to 2 of f at x equal f at 2? And the answer is yes. We determined the limit to be 2, and we determined f at 2 to be 2. So since we passed step 1, 2, and 3 of the continuity test at the only x value that possibly raised a concern, we can say that f is continuous whenever x is a real number.